Okay, something is wrong with the universe because the mic works and the projector worked from the first time without any tech name. So my name is Andrey Vykhodtsev. I work for Microsoft. I live in Slovenia, Ljubljana. And I am a solution architect for data and AI working with Microsoft partners. So I'm helping Microsoft partners build cool things on Azure using deep learning, machine learning, things like that. So I want to first set the stage and tell you when we talk about AI, actually we are not trying to build something like this, right? Otherwise we would have had a visit from Sarah and John Connor already, and then we will be in trouble. And so we are trying to build something that assists humans, which is a weak AI, so we call it. Microsoft has done a lot of breakthroughs in this area. So I have put some useful links for you here. So you want to check out probably the cool blogs. I want to tell you something from 2016. If you remember, there was a competition called ImageNet, and also there is a competition challenge that Microsoft puts out called Microsoft Object Recognition in Context, Microsoft COCO framework. So Microsoft first of all won the ImageNet context in all the four categories for image classification, image segmentation, image localization, and also it is performing as the best model on the COCO framework challenge. Right, then in 2017, Microsoft also did a breakthrough in a general question answering area. So there is a general data set out there called switchboard data set. It's made out of 20,000 telephone calls. And Microsoft did really well and actually broken down the human parity level on that data set, making this 5 or so error rate. Then in 2018, we actually did well also on the reading comprehension data test. So I will show you a little video about this in a second. So we broken the human parity level on the, let's say, on the challenge of reading texts and answering questions about the text. Right, and then this year we did also a machine translation breakthrough. So we broke human parity in. We actually performed better than humans translating text from Chinese to English. Right, so I would like to show you a little video, and actually I invite you to check out this site because it's a very cool site where we put out all the latest projects in the area of AI. So I would like to show you one which is about text comprehension. So do you have a sound?
Which one the touch the night to Marta?
I'm Trivedi. I'm a data scientist in the Microsoft's Cloud AI platform team. I work on developing deep learning models and bring innovative technology into Microsoft solutions. We work with very complex data sets like images and text. A machine reading comprehension, more commonly known as MRC, is a technique where you introduce human-like reading parity into paragraphs. In search, you usually use keywords and the TF-IDF concept where you're ranking the documents, but you're not actually grabbing the context lying in the paragraph. Whereas MRC, you're trying to grab the concept part and trying to answer the question in a more human-like way. What we want to do is have tools which can help us jumpstart in the journey. Microsoft's Cloud AI platform helps you do exactly that. A couple of years ago in 2016, Yalongchen's team was able to introduce a model called Resonant. And we were able to build a fantastic app using this model. Here, you can actually give a contextual paragraph and ask any type of contextual question on that paragraph. We select an excerpt and ask questions against the contextual paragraph. As we see, the Resonant algorithm can very well capture the underlying concept from the given paragraph. It can answer simple questions with intents like who or when very efficiently. Microsoft researchers have been able to take this innovation even a step ahead and introduce the concept of RNet. RNet surpasses human-level parity on squad dataset. It actually introduced the concept of gated attention-based neural networks for the first time, which takes into consideration the nested context from a paragraph. For example, it tries to grab the subject, the predicate, the conditions embedded in a question from the paragraph. Taking all these four concepts together, RNet is trying to grab in an attention-based gated model all the nested concepts and trying to bring that together in a final answer highlighted in red in the paragraph. Microsoft is innovating in this machine reading comprehension space. We are coming up with breakthrough AI innovations in every aspect of the field. So stay tuned with us to see how we are innovating this whole AI space.
There are many more videos like this at this site, so I invite you to check it out. So, how all this is done? All of those applications are powered by something which is called deep neural net. And these deep neural networks, they are applicable in many areas, so the slides that I will be showing next, they are mostly focused on the image analytics and video analytics. So where do you apply deep neural nets? For example, if I focus on video analytics, you can apply it in a law enforcement, public safety, actually determining if the people are fighting in the network, just simply counting actually people in the airport and in public areas already has a lot of applications in different spheres of human society. For example, even in the bank, it's pretty important to know how many people do you have now in the branch. So there are algorithms that allow you to actually automatically count people, monitor, track people lawfully, right? So we also want to take care about, want to be careful about being ethical and building applications like this. So in public monitoring, there are also numerous applications. You can actually analyze automatically images and determine if the car is going the wrong way, determine collision detections to dispatch some forces to the road. You can automatically detect if the person, if the pedestrian is all of a sudden came on the road and there is a problem. Also, you can determine unfavorable conditions. And we actually have built a demo like this. I'm not sure if it is working or not right now, but it is available online, where you can actually automatically look at some roads in Redmond, Seattle, and where you can see some analytics about what is happening on that road. Then actually in medical, in healthcare, there are really numerous applications. You know, from video analytics, you can determine the person, whereas the person has fallen from, for example, from the bed, or you can actually see where is the stuff in the areas in the hospital. But these are only video analytics. I'm not on that slide. I didn't cover, for example, a task of medical imaging. Microsoft is doing actually a lot of projects in medical imaging. So there is a whole branch of Microsoft Research that actually does. There is a program called Microsoft Healthcare Next, where we invest into projects like this. One of the projects is called Project Andrey, where we built the medical imaging system, and that's actually more of an application for medical practitioners when they take the radiological images, and the images, they show 2D snapshots of the tumors, right? So what we are doing, actually, we are reconstructing in the application 3D versions of the tumor, 3D image of the tumor, allowing them to more carefully plan the surgery of the tumor, and actually do a lot of other useful things. So this was even DA approved, I think, in the beginning of this year. But this is Microsoft, right? This is a research project, so it is mostly non-commercial. So this is another example of some project that our partner is doing. So there is a partner called Iris, but their site is also called retinascreenings.com. So they built an application that allows allows for the early detection of the diabetical retinopathy. So when people are diabetics. They have a risk of actually losing their sight because of the retinopathy, and their application allows actually without any intrusion. So previously this kind of test actually took so long and it was really unreliable. So they built an application with the computer vision techniques and with deep learning. They just send an image of an eye and then they get back the potential diagnosis of retinopathy or not. So this slide here is mostly for reference for you. So if you will be, actually one of my goals is to inspire you, if you are a Microsoft partner, to build such things on using our products. Right? So just to go quickly into basics, how all these things are done. And I'm purely focusing here on the computer vision, right? on the deep learning and on the applications for imaging. So traditionally, actually, this was not new. So the computer vision applications are there for a long time. And traditionally, it was done using just computer vision techniques, right? So there are libraries out there like OpenCV, and you can take them, and without any deep learning, without neural nets, you can actually achieve pretty impressive things. For example, I know some libraries that do license plate recognition. They are not using any deep learning, and they work pretty in real time without any neural networks. But then there is, these computer vision things, their drawback basically is that you have to do everything manually. So you have to extract all the information from the images yourself. You have to write a really big program that determines the corners, determines all sorts of things, and then you maybe run a model. But before that, you have to feed that model a accurate representation of what is happening on the image. So deep neural nets were a breakthrough because they actually spare you that work. So they are kind of a vacuum cleaner that just actually sucks in all the features from your image, and it determines really itself what is important or not. And when people actually say deep neural networks, they really mean networks with more than one internal layer, right? Which is pretty, but also it is a really cool way to say it. So in essence, how does that work, right? So you take the images and you feed them to some sort of neural network. And the neural network typically trains, so it has, as an input, it has your data, and it has basically some function which tries to optimize, which is called loss, right? So this is something that we try to minimize. And then we also have forward and backward passes, so we update the weights and then we update them back, so to trying to minimize the loss on each pass. And then recently there is, we apply also a technique called convolutional neural net. So traditionally the problem was that with deep neural nets you had really fully connected layers, and they had really a lot of parameters, and they were really heavy to train. So now we mostly use convolutional neural nets, which are kind of like a filter that applies to an image, and it's basically the weights that come out of it. There are much less weights, right? And then also it uses, as an intermediary steps, it uses the downsamplings like techniques like pooling and so on. To actually the goal of this all is to optimize, is to minimize the weights. So how do you develop a deep learning model? Well, the answer is sometimes you don't have to develop a deep neural network model. So our hope actually is to provide this to you as a service, right? This is why we are building all those cool things, and we are putting them out as a let's say as a pluggable APIs. Right? So you have Microsoft product called Microsoft Cognitive Services that you can actually you can see there is a pretty large catalog of like already 30-40 services. So they are broken down into categories. For computer vision, you have, for example, face recognition, you have motion detection, you have object detection. You can actually mark objects and actually determine on an image where these objects are. And without any training, any network yourself, you can have this functionality in your application, which you will actually plug via the API. But what if you have to actually do a deep neural network yourself. Right? What if there is no other way, and what if none of the services that I just showed you actually will do the job? So this is how you do it, and in a very broad strokes, you prepare the data, you build and train some model, then you deploy your model, right? So the model is just one piece of the equation. Once you have the model, actually there is a big part of the job how to actually productionize that model so that it works in a business setting. And we help you with that with, first of all, there are on top level, there are cognitive services that allow you to have pre-built models, and then there are services that allow you to interact with your models. Then there is infrastructure that actually helps you to store the data, to pre-process the data, to actually do all sorts of infrastructure things on your data. And then there is the lowest level, which actually allows you to have compute, which is CPU, FPGA, GPU. And about the FPGA, I'm going to talk a little in a second. And then there are tools actually that allow you to connect to all of those. So we've come a long way from making you use our tools. Now we have a concept, actually, they allow you to use whatever tools you like to work with our infrastructure. So in terms of the development process, how does it look like? So you have a data, which typically resides somewhere in a data store. And the data store can be a simple database, or in case of images, it can be Azure Blob Store or Azure Data Lake. Then you have your model, you are using your tools. So nowadays I'm preferring either PyCharm or Visual Studio Code. Then you develop basically something that takes this data, applies some models, trains the model. For example, if you are using a framework called PyTorch, this is what you will use. Then once you have your model trained, then you will basically publish your model as a container. You will register that image, and then the model actually can train as a container. You can send it to train somewhere on a service, on a remote machine, or on a remote service. And when it is trained, actually you can get that container and publish it as a model, so that the new, for example, images they get when you have it in a production setting. So it really fits this API that is built around this container an image, and then it replies with the response. So just to build a model is only one step. You have to also have some sort of development life cycle for your models. Right? So when you actually train your models, it's pretty important to monitor how it is going, how the training is going, how actually do you keep the register of the trained models, how well they perform, how do you manage the retraining, and so on. So just developing it in your local environment is just one small step. And you will notice actually quite quickly, if you are trying to do even a project of moderate complexity, that it becomes a problem even on your machine to manage your trained models. Right? I have that problem as well. So when you train your models, you have to have a simple process to actually publish it. Right? And we have developed a process for you which simplifies you publishing the models via the Docker containers. So basically what you build a Docker image that you publish, and then you can actually plug that image to even an on-premise device, we call it Edge, and then connect it to other devices. So when you publish the model, and when you score the model, by scoring I mean actually feeding the model with new data and getting a response, you have to also make it fast, right? And one thing that helps making it faster is hardware acceleration. So we have assessed in the past many ways of accelerating the deep neural network models, and we have chosen FPGAs for many reasons to accelerate the model inference on a scale. I will not go into details why we have chosen FPGAs, but I will show you actually one reason later on. First of all, they are quite less expensive. They allow you to actually have a really high performance on the low batch sizes, and I will talk a little about this. So I will first have to show you just a little, let's say, customer evidence video.
also a contract manufacturer. We are more than that. We're a manufacturing solutions. People tend to think of Jabil as a contract manufacturer. We are more than that. We're a manufacturing solutions provider. It's a very difficult business. We help customers with taking a product and building it at scale.
We went to the production site and found out the test machines suffers very high false call, around 30%.
Operators have approximately 2 seconds to analyze each one of these images. For some of the boards, they can have upwards of several thousand components on it.
Human gets tired constantly staring at the same stuff. We thought that was a very good opportunity for us to use deep learning to classify images. The model is actually reducing the workload for operator. For model training, we're using Azure Linux GPU VM, and we're using Azure Machine Learning Services to deploy the model as Docker container. Our pilot is predicting 75% of the past images and can correctly predict 92% of the defects.
It's one of the most advanced predictive projects that we've had going on so far. We've been talking with Microsoft about Project Brainwave.
The early test result from Microsoft has shown FPGA is capable of predicting 550 images a second, comparing with a CPU cluster with 40 images a second.
The potential for Project Brainwave is substantial in allowing us to move forward at scale for machine learning across Jabil. Very exciting.
So, the term Project Brainwave, this is the code name that we used when we were developing this PGA acceleration for deep neural net inference. Wait a second. Want to go to the next slide?
The potential, very exciting.
It's very exciting. Yes. So the idea of the Project Brainwave is basically you have another framework which actually takes the weights from any of the frameworks that you like to develop your deep neural networks with, for example, TensorFlow, Caffe, and then you just plug those weights to a, let's say, special, another Python SDK that actually helps you to publish them on FPGAs. So you can actually register for a private preview and have that try to build something with it. Just to give you another reason why would you actually go into something like this, right? So if you want to publish a model, and if you want to do it on GPUs, the GPUs, they are quite performant, and they can be quite on par with FPGAs, but they prefer really high batch sizes, right? So you have to pack your images together and feed the GPU that it has really a lot of images together, so it will have good performance then, right? For FPGAs, you don't have to do that. It performs quite well if you just have the batch size of one, and you can see it in the graph. I also have some really GIF file with a demo, but I will not have time to show that because it's a few minutes. So you can actually go to that link, register for a preview, and then try to build something with it. It has a set of Jupyter notebooks and Python to start with. Then, to finish, I would like to talk a little about the edge, right? Because the cloud is great, and actually it's quite good to use the cloud because you have a lot of compute. But also sometimes you don't have the connectivity and you have to do things on premise, right? You cannot really move the data to the cloud. And then you have to use something we call intelligent edge. So we are trying actually to make the experience as smooth as we can, moving stuff from cloud to edge and back. I will pause those slides so to not go over. So this is how you would do it, right? So we have basically the same system when you train your model, when you keep registries of your model in the cloud, but actually the model can run on premises, on a SDK. And I will tell you about this SDK in a second. Historically, the problems here were around integration, right? And there are still a lot of problems because you have a lot of software SDKs, you have a lot of hardware, and it's kind of hard to make it standardized. So we have tried to partner with Qualcomm to make it let's say, SDK, a vision development kit for AI development kit for vision problems, which is a camera basically paired with the FPGA device. So to wrap up, I hope I have shown you some cool cases and have inspired you to try to build something with Azure. I posted some links to the previews, then where you can actually post those links and see actually the projects also that we are doing. So if you are a partner of Microsoft trying to build something with AI, you can reach me and I can connect you with someone or maybe help you. So this is it. Thank you.
Do you have any questions? Yeah.
I didn't quite understand why FPGA is so effective with a batch size of 1. Does it have direct access to just normal RAM on the computer, or how does this all?
So FPGA is a special board, right? So it has basically a different design. So the design of FPGA is basically programmable as CPU. It has a set of instructions to reprogram the CPU itself as different, let's say. So there is a something called hardware DDL, I don't remember. I used to actually program some of those things like 17 years ago. I don't remember much. Basically, it's a separate device. They are typically produced by the companies like Andrey and so on. One of the things they are really parallelized and they are reprogrammable. So you have to. Actually, they were used for a really long time in Azure for software-defined networking. So you can really program a software, let's say, network switch with this FPGA device. And then they really consume not a lot of energy. And then they have also, like GPUs, they have internal parallelism. Right? So if you looked at the slide quite a while back, there were like CPUs, GPUs, FPGAs, and ASICs.
My question is about how it's related to RAM. How does it communicate to RAM? If you don't know.
You mean physically? How it is connected?
How does communication to RAM give it good performance? If you can answer, great. If not, answer.
No, I know from, I don't know how that one actually physically connected to RAM, right? So in my previous life, I think FPGA typically connects to regular RAM via PCIe. So it's another board in the machine, which is connected via PCIe interface to the machine. Then it accesses the main RAM on the board.
Yeah, but then that would be the same problem the GPUs have.
But it also has its own RAM, right, on FPGA. Well, the answer is I will not dance around. I don't know exactly. Yes.
But we have been a Microsoft partner for some time now. Unfortunately, we are moving away.
Okay.
And that's why I was very interested in your presentation. The problem that we are facing is things are moving back to the olden age where people are moving away from cloud. And most of the clients that we work with, they have their own private cloud or they have their in-house data center, and it's completely edge-based now. So where we're using a lot of cognitive servers from Microsoft, now we are actually forced to develop because the cognitive servers won't work without me putting it in an Azure open cloud. So how closer are you guys to really going edge, or if not edge, at least making it work in a private environment?
Well, I wouldn't say that all of the services that we have now, they work on edge, but we actually are moving that way because we have, for example, we introduced the custom vision service, which allows you to do object detection. For that custom vision service, you can plug out the model in a format called NNX. So NNX is a project for portable, let's say, neural network weights. Right? You can export that model and run it on edge, or actually export it as a Docker container and run it on edge. So for some services it works like this.
So basically, the Vision Kit is going to be your first actual product where we can do a real edge-based networking.
Yes, and they actually have on-premises products for machine learning. For example, there is a machine learning server which supports Python and R. Right? So if you want to use that, some people actually like to use that.
Okay. I'll connect up.
Question on there?
Hi, so just to add on to the question about FPGAs, so I was wondering, you mentioned you're using FPGAs in inference, so what about training? And
we don't use at the moment PGAs for training. I am not sure if it, if you actually watch the video, right? So they clearly said they're using GPUs for training, and they use a PGA for it in training. The reason I believe is in this. The reason was shown at when I was talking about the batch sizes, right? So with GPUs, you can probably have, you can actually do it more performantly, and if you pack the images together. So PGAs are for reference, but we also have another example that I didn't show today. So, for example, we have AI for Air program, and where we actually did a large-scale classification on a map. Basically, they provided 1 meter, let's say, size tiles, and we did with the PGAs. We did basically classification of the whole map in like 20 minutes. When it was GPU, it would take several days, to classify this. So you can call it probably training of some sorts, right? But still, it is only for inference.
Thank you.